Okay, basic principles of mammography. Actually, mammography, as we all know, it is a radiographic examination of breast pathology, and interest in breast imaging has been fostered especially after the realization that approximately 1 in 10 women will develop breast cancer after the age of 45. So the technology advancement over the last several decades have occurred in diagnostic imaging over the sensitivity of mammography in breast imaging. So in breast imaging we have direct film exposure and digital and zero mammography, that is using Xerox film. So in fact it is possible that early mammography screens in 1950s and 1960s only developed with the realization of breast cancer. And now we have American College of Radiology, which is improving this examination. So mammography is a special type of imaging that uses low dose X-ray systems to examine the breast. And here we use the low dose of ionizing radiation, that is X-rays. So these include 3 types, that is digital mammography, computer aided detection, and full and breast tomosynthesis. So digital mammography is also known as full field digital mammography, in which the X-ray film is replaced by the solid state detectors that convert the X-rays directly into the electrical signals. So these detectors are similar to that found in the digital cameras, and the computer aided detection CAD uses a digitized mammographic image that can be used from either conventional film mammography or digitally acquired mammogram. So after the computer software then searches for the abnormal areas of density, masses, and the calcification that may indicate the presence of cancer and the breast pathology. So breast imaging and breast tomosynthesis, also called as 3D breast imaging, is a mammographic system where the X-ray tube moves in an arc over the breast during the X-ray exposure. So it creates a series of thin slices of breast through the pathway where the X-ray tube moves. And in views of mammography, we usually use 2 views, that is MLO, medial lateral oblique, and the craniocaudal CC view. So breast cancer screening programs depends on the X-ray mammogram. And here we have the features of breast cancer, that is speculated margins, cluster, microcalcification, architectural distortion of the breast, etc. So this is the MLO view, and here we can see the V shape of pectoralis muscles, and this is the CC view. And you can see oval. And in compression view, we compress the breast tissue of desired region of interest. This is the magnification view, where we magnify where we want to magnify. So this is the CC view and the oblique view. Coming to the history, it goes to the 1913, where the radiographic appearance of breast cancer was first reported. Then in 1950s, the industries began to develop the X-ray film, especially the Agfa Fuji, and in 1960s the xerography with low dose was used, and in 1966 the first sophisticated mammography system which we use today was introduced. In 1975 the film was again developed into the high speed and high resolution. And in 1992, the mammography quality assurance was implemented. So this actually what happens from the X-ray tube. The X-ray tube emits the X-rays, then those X-rays strike the breast tissue, and from the breast the transmitted X-ray beam again strike the phosphorus screen and the film emulsion, then the film is processed. So why do we need compression in breast imaging? That is, it decreases the thickness, it decreases magnification, reduces scatter. As the thickness is decreased, increases the contrast, that is the difference in density for a given region of interest, for a given change in exposure is increased. And it also reduces the motion on sharpness as it decreases the subject thickness, and it also reduces the exposure as the thickness is decreased. So what is Mammography Quality Standard Act? What it does? That means it formulates the formal training and continuing education, regulate inspection of equipment and documentation of quality assurance. That means how we can control the good mammographic film, and report means the reporting results of follow-up, tracking patient and monitoring outcomes. So this is the mammographic X-ray tube. Here we can see the X-ray tube hanging at the top. There is the tube port, and in the tube port just below there is the filtration. We use the 0.5 mm aluminum equivalent filter, and in mammographic X-ray tube we use the beryllium filter of atomic number 4 because we use the low X-ray energy. And there is the compression paddle, grades, and the screen film system, and the photo timer detectors for the exposure time. So what is the design of the anode? Initially it was also the stationary type, but after the development of rotating anode in 1988, the molybdenum is the commonest material for the anode, and here we can also use the rhodium and tungsten. The characteristic K is of the molybdenum is 17.5 and 19.6 kilo electron volt, which we can see spiked in the graph just little bit after. And there is the rhodium, which has the K characteristic energy of 20.2 and 22.7 kilo electron volt. There are two numbers because in the K shell we have K alpha 1 and K alpha 2, because when the K shell is filled from L, then it's from 1s orbital, then we have K alpha 1. When it is filled from 2s orbital, then we have K alpha 2. And there is the SID, that is source image distance of 65 centimeter and the anode angle of 20 degrees, so we can cover full FOB. This is how the anode angle affects. So what is Hill effect? Everybody knows here that the Hill effect, the X-ray intensity in the anode side and the cathode side is not the same. Cathode side always have higher X-ray intensity than the anode side. If at the middle we have 100% X-ray intensity, the X-ray intensity may decrease up to 70% in anode side and may increase up to 140% in cathode side. So utilizing the Hill effect, we can put the higher thickness of breast near to the chest wall in the cathode side, and the anode side, the nipple region having lesser thickness in the anode side. So what kind of focal spot we desire? We especially desire the point focal spot of 0.3 or 0.4 mm for non-magnification, and for magnification the focal spot is also reduced to 0.1 to 0.15 mm. So combining this, we can have the dual focal spot, that is dual filament in a focusing cup, that produces these two type of focal spot. And it is very important that the medical physicist design the focal spot for the appropriate and excellent best image of the X-ray film, that is mammographic film. Because the mammographic film operates at very low doses, especially below 35 kb, so we require very compact type of design. So this is how the anode angle affects. So we use the beryllium window, that is the inherent filter, and the added filter or the additional filter of aluminium. So in mammography we especially use the characteristic radiation. We try to avoid the Bremsstrahlung radiation, that is the continuous radiation. The braking radiation when produces the which are produced when the electron goes near to the nucleus but do not strike with the electron. So the optimal X-ray energy is achieved by the use of specific X-ray target material to generate the characteristic X-ray energy of 13.17 to 23 kiloelectron volt, and the X-ray attenuation filters to remove the undesired, that is Bremsstrahlung radiation. So we can use molybdenum, rhodium, ruthenium, which generate the characteristic X-rays in the desired energy for the mammogram. So of all these material, molybdenum and the rhodium are used for mammography X-ray tubes, which generate the characteristic X-ray energy of 17.5 and 19.6 kiloelectron volt and 20.2 and 22.7 kiloelectron volt. So here is the graph, the above one, which shows the Bremsstrahlung radiation, that is continuous radiation, and the middle there is the characteristic radiation of nearly 17 and then 19.6, and this is the combined one, composite one. So these are the how the characteristic energy radiation are produced from molybdenum and ruthenium. Especially below 17 nothing happens, no X-rays are produced, but suddenly when the 17 kiloelectron volt is reached, there is the abrupt change in X-ray intensity. And for rhodium also there is the same. When it reaches the 24, there is sudden increase in the X-rays. So here the common filters used in mammography are the 0.03 mm thick molybdenum for molybdenum target and molybdenum filter. This is the unfiltered one, and there is the maximum number of continuous radiation, which we do not want to desire, which we do not need. So this at the left side of the characteristic curve, they only increases the patient dose, that is the radiation dose to the exposure, and the characteristic peak which we actually desire for imaging. So here this used undesired radiation is now filtered. Here we do not see the such half circle type. So the area under this curve is reduced. That means it is filtered one. So the more we filter, then the less we are giving radiation dose to the patient. So for this we need to consider the appropriate filter. That the dotted peak is for the molybdenum and the solid line is for the rhodium. Here molybdenum has lesser characteristic radiation peak than the rhodium, because the rhodium has higher atomic number, so it is shifted to the right, and molybdenum having 42 atomic number have lesser. So these are the targets and the filter. For molybdenum we have 17 and 19 keV X-rays and bremsstrahlung up to 20 kilo electron volt, and it gives the best contrast for moderate, thick and dense breast. For molybdenum rhodium we have 17 and 19 plus bremsstrahlung up to 22. It reduces time and dose for the thicker and the denser breast. And for rhodium tungsten rhodium, we have 19 and the 21 keV X-rays. It also reduces the time and the dose for the thickest and the densest breast. So the increase in exposure output is roughly proportional to the third power of the keV, that is kilovoltage, and directly proportional to the atomic number of the target. That means which target we are using. For example, molybdenum, the atomic number is 42, and for rhodium it is 45. Collimation, the collimation should match the field size. Actually in mammography we do not collimate, but the collimation is equal to the field size of the cassette. Generator, we desire high frequency generator. Photo timer, automatic exposure controller detector is located underneath the cassette in mammography. So this is how we manipulate the kV and MAS, but actually I will better describe in the exposure timer, which I have already described. Conventional mammography, the film is single emulsion in conventional mammography. In conventional mammography, the X-ray film is exposed, and it is the same principle as in general radiography. There is the silver halide crystals, and the silver halide crystals form the latent image which need to be processed, and after processing then the final mammography film is ready for visualize. So how can we reduce the scatter radiation? First of all, we have to use the compression for scatter radiation. Then we have fixed grids, bulky fiber air spaces, and high tension cellular grid, high transmission cellular grids, which is the latest one, and grid motion is one pass or reciprocating. So in A, that is the linear grids. Linear grids means they are of single lines, not crossed. And in B, there is the cellular grid of mesh type of boxes, which is more efficient. And in C, we only increases the distance so that less scatter reaches the X-ray field. 5:1 ratio means it's the lead material, and the interspace is 5:1. Material is 1. For example, the interspace is 5 mm, then the lead strip is just 1 mm. This is the characteristic curve of the mammography film, and in direct film we have higher exposure, and in moderate the exposure is little decreased, but nowadays for little exposure also then we can have maximum optical density, which is very good actually. So these are the high transmission cellular grids, which can also increase up to 23 lines per centimeter. So in mammography, first of all, the breast tissue is X-ray, then the pattern of the X-ray information is located in the phosphor, and after reading by light, helium neon laser light, then we can have the analog image. But in mammography, in full field digital detectors, the breast tissue after exposure is the X-ray information are directly located in the detectors, and in detectors the X-ray information is directly converted into the electrical signal, and we only need here the analog to digital converter to form the image, which is actually done in the computers. So what is direct and indirect? Direct conversion means the X-ray information is directly converted into the electrical signal. We don't need the intermediate use of light photons in between. So the X-ray information after X-rays we can have direct the image. But in indirect, the scintillator phosphors, where X-ray information is first converted into the light photons, then again into the electrical signal. So in direct conversion we have amorphous selenium, which is a semiconductor, and using thin film transistor or flat panel technology, using Siemens or holozoic, we can do this process. Holozoic is actually, we are watching World Cup today, so holozoic means we don't need to see live in the TV screen. Actually it seems like it's happening just near in front of us, just like we are seeing this is the stadium and we are watching here. That type of technology is the holozoic. Indirect conversion, here we use the scintillator phosphors, that is cesium iodide, on an array of amorphous silicon photodiodes using the thin film transistor or flat panel technology. And nowadays there is also the LCD, LED, OLED technology. In LCD technology there is the same. There is the cathode or fluorescent tubes behind the screens, and in LED there is the every pixel have brightness, that is the OLED. And for we can control the brightness of every pixel in the OLED technology, and every pixel has the sub pixels for different colors, red, blue and green. So this is the same, the selenium X-rays, then we can have directly the digital data. And in indirect, first we need the photodiodes. So in conventional the characteristic curve is sigmoid 1, and in digital it is a straight line. So there is the linear relationship between the exposure and optical density in digital imaging, which is very easy to manipulate and processing. But in conventional, we have to know the particular threshold after which the density increases and after which the useful density vanishes. So in between the straight lines, vertical straight lines, that is the useful density. Thank you.
The T